You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech Podcast. My guest today is Creon Levit. He's a director of R&D at Planet Labs. And Creon worked for 32 years at NASA Ames Research Center in Silicon Valley. He's now the director of research at Planet Labs, where they build, launch, and operate the world's largest constellation of satellites to make change on Earth more visible and actionable. So we'll get into what that means. But Creon, thanks for coming.
Oh, my pleasure. I've been looking forward to this.
Yeah. So, how many satellites have been launched by Planet, and are they in what kind of orbit are they in? Like, what are a few details of the constellation?
Okay. Well, that's a bit of a complicated story, but basically, Planet has launched well over 300 satellites. Although we do not have that many in orbit right now. We have, I think, around half that many in orbit right now. A number of them were launched a few years ago into very low orbit. They were just for testing, and so they have re-entered the atmosphere and burned up. But we have actually sort of a meta constellation up there now, built of multiple sub constellations. I could pull up the exact numbers if I need to, but we have about 150 small, microsats up there, CubeSats, but they're quite powerful. And then we have another constellation of larger satellites of similar power. And then we have also the world's largest constellation of high-resolution imaging satellites. We have 15 SkySat satellites that we got when we acquired the company Terabella from Google. We merged our two companies, and they had a fleet of 5 high-resolution satellites in orbit, and since then we've launched 10 more. So these are all Earth observation satellites, but they kind of run at different resolutions and different cadences. So the high-resolution satellites that are in they're all in low Earth orbit, various altitudes from, say, 350 to 450 kilometers. And the high-resolution satellites image various targets on the ground, sort of by pointing at them, thousands of targets per day. And then the lower resolution satellites, which are in greater numbers, the smaller ones, they image all of the land area of the planet every day, and coastal waters and islands and things like that. So we like to say we image the whole planet every day, but it's actually the day side of the planet, and it's mostly land and coastlines.
So when you say different resolutions, like what is the highest resolution that you have? Are there higher resolution satellites out there that are like government satellites that are secrets, or what could you say about resolution?
Well, I can't say anything about government secrets, of course, but what we call medium, we talk about our medium resolution satellites and our high resolution satellites. And our medium resolution satellites image the Earth at around 5 meters per pixel, and in multiple spectral bands, 4, 5, or 8 spectral bands, depending on how new they are. So each pixel is roughly 5 meters square on the ground, and gets imaged in a bunch of visible and as well as in near infrared colors. And then the high resolution satellites, they have a resolution of about 80 centimeters per pixel. So let's see, that's about around 3 feet. And there are higher resolution imaging satellites in orbit, even ones that are unclassified. There's one in particular named Worldview 3 that can image at 35 centimeters per pixel. It's like $1 billion satellite. Uh, and the US government buys a lot of that imagery, but other people do as well. But we have 15 satellites in orbit that can image at a little less than half of that high resolution worldview. As for the top secret government stuff, we could just assume that they are at least as good as the worldview 35 centimeter resolution and perhaps better. In fact, almost certainly better.
Do you think anyone's got the technology out there to do like 1 inch or 1 centimeter resolution per pixel?
No, that's pretty much prohibited by the laws of physics. Things like atmospheric turbulence and atmospheric scattering and just the wave nature of light means that can't be done, or probably can't be done. Yeah.
And what do you think the wall is, the threshold, the limit for visible light?
As I understand it, the threshold is probably around maybe 6 inches on a good day, on a perfect day with still cool air and just the right lighting and everything in perfect working precision on your satellite. Then you might be able to get a 6-inch resolution, but oftentimes not. Okay. Like everything that happens just conspires to mess it up, right? If the air is turbulent, or if there's any haze or clouds or smoke, or if there's anything out of adjustment on your satellite, it always gets blurrier. It never gets sharper.
Yeah. So how about all right, so the images, you guys are looking every day at land masses and water, and why look at things every day? Is there very much change day to day in things? And what do you see that's interesting that happens on a day-to-day change basis?
Well, of course, that depends at what spatial scale we're looking. If we're looking at high resolution, we tend to be looking at areas where there's a lot of human activity, and that changes on a day-to-day basis. Business activity changes on weekly and seasonal cycles, and we can see that to some extent by looking at all kinds of indicators of business activity. Industrial activity as well similarly changes. You can see if mines are running or not, and if power plants are running or not, and if ports are busy or not, and how many ships are coming and going. You on the medium resolution side, that is more like agricultural situations. So we can tell the health of crops, and we can tell the state of forests, and we can tell kind of land use, and we can see construction projects going on. And so that stuff, larger scale stuff does tend to change a little more slowly, right? Or usually, unless there's some giant forest fire or something. And that might make it seem like, well, why bother imaging every day if stuff doesn't change every day at that scale? But one thing to remember is that half the time, on average, it's cloudy and you don't see anything in any given location. And some places are cloudy a lot more than half the time. So even if you look every day once, you might only get a clear shot every week.
What about climate change? Are you able to see evidence of it or no evidence of it? When you look at certain ice movements and land movements?
Absolutely. We image actually, because of the orbits of our satellites, we tend to image the polar regions more frequently than we image the rest of the Earth. So when I say we image it every day, that's just near the equator where we have the sort of sparsest coverage. All the orbits kind of converge near the poles of all of our satellites. So we get higher coverage in the polar regions, and we have special exposure settings for imaging the highly reflective ice and snow at the poles. And so, yeah, we see all kinds of evidence of the ice moving and the ice changing, and daily, seasonally. As far evidence of climate change, we've only been up there for a couple of years, so it's hard to say from our data set alone what it says about climate change. One has to generally go back to the more long-term, lower resolution government data sets from like the Landsat satellites and things like that, so that you can look at 20, 30 years worth of data for and high precision data for climate studies. But we see all kinds of environment. We have many users in the government and in environmental organizations and other governments and scientists and university students. They all have access to our data or can obtain it. We have site-wide licenses for universities and things like that. And so people do all kinds of studies on climate and ice flow and species diversity and land use. So yeah, there's a lot of environmental uses for these data.
Yeah, that's what I was gonna say. Is who uses the data and why? Maybe, like, in your opinion, what are some of the most useful things that have come from the data?
Well, there are really, I would say, three broad classes of data use, and one might be called, well, let's say four classes. There's obviously, government and intelligence kind of use cases for remote sensing data, and then there are commercial use cases, such as we were talking about before, like business activity and agricultural activity, and predictions of future crop harvests, and ways to tell farmers, what fields need what kind of treatment and how they're doing. So there's government stuff, there's kind of agricultural, commercial stuff, including insurance, and then there's environmental use cases, uh, including human rights use cases, where we can, we have several situations where we've seen evidence of human rights violations or military activity that governments have denied, and yet were clearly visible, and that hence they were accountable and they had to be more transparent. And then that kind of overlaps into scientific use cases, right? Where, as I said, climate, just studies of ecology, geology, all sorts of things. So there's a lot of different use cases and a lot of different customers. We have a growing set of customers, markets expanding as people figure out how this data can be useful.
Interesting. I know where is the technology going? Are you going to be? I mean, well, all right. There's a couple questions in here. How much data is generated from the images you're producing, and are you able to get everything you want out of the data, out of the images, or do you need like large scale processing of it because there is so much? What's to be said there?
Well, that's a really good question, and it's a rather deep question. So, in terms of the raw amount of data, we download, I believe, around 7 terabytes 7 terabytes a day of image data from our satellite constellations, and we are actually, I believe, required by law to maintain copies in perpetuity of all the data we download.
Okay.
And then, but that raw data is not necessarily very suitable even for looking at, because there's all kinds of calibrations that have to be applied to it, and it has to be sort of mapped onto the surface of the Earth so that people know exactly, can find it and know that it's accurately registered, and so that you can look at stacks of data over time, because that's a big application. But obviously, no one's going to be looking at 7 terabytes of image data a day, or even if they're looking at just one spot, we're shooting it every day. And so the amount of image data is kind of overwhelming for all but the smallest regions of interest. And so the processing is kind of where the action is now. Like, the question is, how do you turn a bunch of images or stack of images or a huge map of images into something actionable? And so that really depends on the user's applications. And some users do it themselves, and sometimes we provide the basics in an API format for them to do image classification and object recognition, things like that on the data. So, for instance, you can look for all roads in a certain area, and you can look for all roads that have been constructed in the last 6 months in a certain area. And then you can make a graph of how many there are and things like that. That's just one application use case. But really, you're onto something there, because most people seem convinced that the future of these massive data feeds is in image processing, machine learning, AI, and transforming the image data into maybe simpler forms of data that people are actually interested in, like how many houses were built or how many acres were burned, that sort of thing.
Okay, I'm thinking of all kinds of. I guess probably the most interesting thing would be time lapse. I guess if you took a series of images over a season and time lapse them, and then looked back 1 season, 2 seasons, 3 seasons, like winter of this year, winter of last year, winter of the year before, and compare the time lapse of all three in a certain region to see if there were different manifestations of winter or different things that
Hey,
occurred during that time.
that's a great idea. So you can sign up for Planet Explorer, which is, I guess, kind of some sort of freemium uh, browser we have, and you can look through stacks of data and you can download them and you can process them. Right now, we're kind of moving more and more away from a download model and more and more towards browse the data and then upload an algorithm and run it on our data in the cloud to produce the results you want, because otherwise, as I sort of alluded to before, it just ends up being a huge amount of data and a lot of process, a lot of data downloaded to a local machine and a lot of processing, or a lot of data transported somewhere else in the cloud for a lot of processing. So we're kind of moving a little more towards a in-place model. But all sorts of models are supported, and everyone is encouraged to try and move on their own inspiration and see what they can do with it.
Any surprising or really interesting use cases of the data that you thought were interesting to you?
Oh gosh, there's so many, especially I guess I'll talk about two that I'm personally pretty jazzed about. The first one is a commercial use case, but I believe it has really profound climate and environmental implications for the Earth, and that is the use of the daily data to tell ranchers where the grass in their paddocks is at the perfect stage to send their ruminant animals out to graze. So if you want to keep the animals healthy and you want to keep the grass healthy and you want to keep the perennial grasses growing so that their roots get deeper and deeper and they sequester more and more carbon and rebuild the soil, and you have to send the animals out to graze at exactly the right time. If the grass is too short, it doesn't work out for the grass or the animals or the soil. And if the grass is too long, same situation. So you have to know that the grass and the soil are at the optimal situation for the grazing, and then you send your animals to that particular paddock. And I think that's something which there's a company in New Zealand that's been doing that with our data, and now they're scaling out to Africa. And I think that this is something that should be scaled worldwide and could really transform the planet and provide high quality food in a carbon negative manner. So that's something I'm very excited about. And then to kind of switch gears, I would say another thing that I'm really excited about is a little more future oriented, and that is the tracking of species diversity in various regions, particularly rainforests, but it doesn't have to be rainforests. As we put more and more spectral bands into our medium resolution and high resolution satellites, it becomes possible to really figure out to some extent which species are living in which pixels, and of plants mostly, sometimes insects, I suppose. And so this is a pretty important thing and a big new field of science that's going to become more and more important if we want to understand globally what's going on with migration and climate change and natural processes, as well as human perturbations.
Yeah, I was going to ask you if you can tag, let's say, a flock of birds and then use satellites to watch its migration, or a herd of animals, or other objects,
By tag, what do you mean?
Well, tag it in such a way that a satellite could pick it out, even though it doesn't have, let's say it only has a 3-foot resolution.
Well, yeah, I mean,
out where the object
definitely, I believe that there's a pretty big system of using radio tagging of animals. They actually literally staple a tag onto the animal that's got a radio transmitter, and naturalists have been using that sort of thing, and farmers too, of course. And I know that there are some satellite systems that can track those RFID kind of tags from orbit. Ours, we don't do that, at least not right now. And as for trying to track animals from orbit, yeah, we've occasionally spotted whales, and I guess we should be able to see the sort of largest flamingo flocks and things like this. That's a good question. I don't really know what evidence of animals we've seen from orbit. Really large herds. Oh, we've seen cows. I mean, herds of cows, but we don't. I don't really know of any great use cases on there. I think some farmer actually lined up all his cows into a funny message for one of our satellites once.
That's pretty cool. And you mentioned other spectra. So visible, I guess you do infrared, you do UV, or like what spectra do you use, and what
We
information have you
don't.
found there?
We don't. Yeah. Okay. Well, we don't really use UV because that's all just scattered by the atmosphere, and so unless you're just interested in high altitude clouds and aerosols, you can't really see UV from the surface. As you know, the atmosphere blocks UV, which is why we don't all get fried by the sun.
Right, that's right.
Even blue light is pretty low information content in terms of what you can see of the ground. If you're looking in the blue spectrum, you look at the Earth, it looks like from space, it looks like a big blue ball. So there's not that much to see in the blue. Red and the green I mean, we image in blue, but the red and the green are the really high information content visible bands. And then there's a lot of infrared. Infrared is, in a sense, much more broad and varietal than visible. Visible is about 1 octave, and infrared is several octaves. And we routinely image in the near infrared. We've sent some cameras up to image in shortwave infrared, which is a little bit more into the infrared. And then there's medium wave infrared and long wave infrared, which are kind of like thermal. And we've actually sent some thermal cameras up as well, but we don't have any products that are shortwave infrared or thermal infrared at this time. It's not to say that we won't have them in the future. We probably will. But other satellites image at those longer wavelengths, shortwave infrared, medium wave infrared, long wave infrared. But as you go to those deeper and deeper infrared wavelengths, sort of because of the laws of physics, the wavelength of light gets longer and longer, and hence the resolution gets worse and worse for a constant size telescope, if you will. It's like the thing which determines the resolution of a satellite, assuming you build it and operate it perfectly, is how big is the telescope compared to the wavelength of light that you're imaging. So a given telescope, say like our SkySat constellation has 35 centimeter diameter telescopes. They have one resolution in the blue end of the spectrum, and then in the near infrared, they have like half that much resolution because the near infrared light is like twice the wavelength of the blue light. So anyway, that's a little technical, but the point is that as you go to the infrared, you either have to accept lower resolution or build a larger, more expensive satellite. And then there's other problems as well with infrared, like you have to start cooling the detectors, or otherwise you get too much noise. So it tends to get more expensive if you want high quality infrared imagery, especially into the longer wavelengths. But that's probably going to get cheaper, and it's probably going to become more attractive for us to fly more of that stuff in the future.
What information do you think will be gotten from exploring the infrared spectrum?
Oh, infrared can do magical things. Infrared can tell you about the moisture content of all kinds of organic material on the ground, alive or dead. Infrared can help you differentiate species, as we were talking about before. And if you chop it up fine enough, like if you have enough spectral bands in the infrared, like very narrow spectral bands, which of course is technically challenging, but certainly doable with enough time and effort. If you have narrow spectral bands in the shortwave infrared, you can even detect gases of interest, such as carbon dioxide, methane, water vapor. And so you can track the emission and transport of environmentally relevant gases, whether they're emitted by volcanoes or humans or the ecosphere. Anyway, so that's pretty interesting. And that has a lot of potential applications. And also with the shortwave infrared, you can determine certain things about the mineralogical content of the ground that you're looking at. And that's interesting, although that probably doesn't change very quickly. So it's not clear that you'd need regular updates on that.
Okay. And you mentioned a way for people to, through their computer, explore the images. Can you restate that again? And I want to ask you for some more follow-up.
Oh, yeah. Well, I think it's planet.com/explorer. But if you just go to planet.com, I believe that it'll point people to the Explorer program. And also, of course, we're always looking for qualified engineers and all kinds of people, hardware, software, spacecraft, domain experts. Yeah, I'd say just rather than me bungling some URL that I can't quite remember, just go to planet.com and look around for Explorer and look around for all sorts of things. We have blogs and use cases, and you can see some of the beautiful imagery. Yeah.
Okay. And the best way to get in touch and ask questions for follow-up is also planet.com. Was there another way to do
it? Well, I mean, we can, I think that's the best way for now. And if someone has I'm a little bit, well, people can find my email address anyway online if they want to talk to me. So that's pretty obvious. Okay. I'm willing to entertain questions as long as they don't get overwhelmingly frequent.
Sure. Okay. Well, that's great, Creon. I appreciate you coming on the podcast. It's super interesting to see what what all this is about. So thank you.
Yeah, you're very welcome. Okay. Well, I'd say that I would say that one is sort of a problem that the space business has. It's a kind of hard business. It's expensive, but it's really fun. One thing that makes our company great is that we are really purpose driven. Like we need to make money and stay in business and make profit, but that is not primarily why we're doing this. We recognize that that's a high priority for us and for our investors, but we're in it to make a positive difference in the world and to make the world a more transparent place and to make change visible and actionable. And so that makes it a really great place to work, and the people tend to be wonderful. An interesting I'm going to skip the problem, but let me just say that another fun thing about the space business, not just for us, but really for anybody, as compared to, say, the software business, and this was said by a friend of mine who worked in the software business when I took her to a rocket launch when some of our satellites went up. We've had well over 30 launches with our satellites on it. And she just afterwards said, at my company, when we do a launch, we rearrange some menu bar or something like that and call it a launch. When you guys do a launch, it really is a launch. So I got to kick that.
That's cool. Very, very cool.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.